So we were looking at revision of waves last time, and this is the point where we had left off, interference of waves. So let's start with another example, problem of that today. So just as a quick review, we've understood that if your wave equations are given such that they are having the same frequency, okay, so the condition for interference is that the frequency is identical. So omega equal to 2 pi f, both the waves are of same frequency, but they reach at a certain point with a phase difference of delta phi. So that phase difference contributes to the resultant amplitude, which is then given by this, or the equivalent formula of root a1 square plus a2 square plus 2a1 a2 cos phi. And to that end, we had seen that if delta phi is an even multiple of pi, then we have constructive interference. Odd multiple of pi, we have destructive interference. All that we've understood. Now, today we are more concerned in this coming problem uh, about how the phase difference can be related with path difference. If there is only path difference, that means the two sources which are creating the waves are synchronized, whereas it can also depend on path difference as well as time difference. If there's a timing difference between the two sources, that means the two sources are not oscillating in synchronization. So let's understand what we mean by that. So this is the problem to relate to that. So we have two simple harmonic sources here, which are, you can see they're oscillating perpendicular to the medium. The medium is along the x-axis, that is your thread or rope, and this source is oscillating along the y-axis. This source is oscillating along the y-axis. So they are both oscillating with same frequency, but they are not at the same position. So you can see there is a distance between them. Okay, let's say this is x equal to plus b. So when you consider a general point like this at x equal to x, the wave coming from this one and the wave coming from this one, they have the same frequency, but they'll not be in phase because there's some distance between them. Plus, according to the first part of the question, there is also a timing difference between the two sources. The two sources are not started synchronously, but one is started at t equal to 0 and one is started with a certain delta t time interval. Okay. So based on this data now, we have to calculate the condition of the given question. So just start by working out this one. So basically you have to find out how you can relate the phase difference with respect to the timing difference delta t and also the distance d between the two sources, and the distance d over here is given to you as 75 centimeters. Okay, so hope all of you are understanding the question. So you can first of all just start by telling me what are the basic properties of the waves that will be created by S1 and S2. That means how much will their wavelength be, what will their wave speed be, then we can come to phase difference. So if you are at the moment you are feeling a little this thing that how to start this question, then start by working out how much is the frequency is given to you of the sources. So how much is omega, how much is wave speed, how much is k, how much is lambda, then we'll come to the phase difference, delta phi, how much that is. Third session of geometrical. So I'm getting some answers. Let me check all the values. Yes, very good. Omega is, wave speed is 200 meters per second, Manishka, that's correct. And therefore your lambda is 1 meter. Okay. So omega is 2 pi by lambda. So in this case, omega will be 2 pi, no matter. Because lambda is 1. No? Sorry, omega is 2 pi f. So correct. That's 400 pi. Very good. So your starting point becomes this actually, that given the frequency is 200 hertz, so omega is equal to 2 pi f or 400 pi radians per second. Given your tension in the string is 8,000 newtons and linear mass density is 2 gram per centimeter, that is 0.2 kg per meter. So your wave speed, propagation speed, square root p by mu, that is becoming 200 meters per second. So therefore now lambda is v by f or 1 meter. So your k is 2 pi radians per meter. Okay, so that is that. So now we come to our wave equations. So if you just think about the source S1 alone, what kind of waves it is creating? It's at x equal to 0, at t equal to 0. So the displacement of that point is E1 sine omega t, where E1 is this at x equal to 0. This is at E1 equal to 1.2 millimeters, and omega is equal to what we have written above. So this what kind of, so this is the source S1 is creating. So what kind of wave it is creating at a point P, which is at x equal to x. So the corresponding wave it creates from the source S1, that y1, the function of x and t, becomes E1 sine omega t minus kx. Very simple. Where omega and k we have calculated above. But in comparison to this, now if you see the second source, that's let's say somewhere over here. So this is at x equal to 75 centimeters. And it starts at t equal to delta t. So it starts with a delay. So on its own, what is the equation of that source S2? It's this. Because it started with a delay. So its starting time is not t equal to 0. So for example, if it has started with a delay of, so if it has started, correct. So far your answers are correct, Manisha. So if it has started with a delay of let's say 1 second, then at t equal to 5 seconds, it has oscillated for how much time? Not 5 seconds, but 4 seconds only. Whereas the first one is oscillated for 5 seconds. So that's why here the omega has to be multiplied with t minus delta t. Because it started with that kind of delay. So the wave it creates at the point P. So this is the displacement it creates at x equal to d. Okay, so the wave it creates, that is y2 at a general point x as at a general time t, is equal to that amplitude into sine omega of t minus delta t minus k, but is traveling a distance of x minus t, like this. So this is becoming a second equation. So now you can see that the resultant interference, so due to superposition, we have our net displacement is y1 plus y2. So it is becoming E1 sine omega t minus kx plus E2 sine, now this kind of a term. Where we know that E2 was 1.6 millimeters. Okay. So this is becoming a resultant, or you can see that plus some phase difference. So that phase difference is basically what is coming from delta t. So you can see here, first of all, how much is that phase difference delta from? Okay. And from that, now find delta t so that your net amplitude is actually becoming A1 plus A2 or 2.8 millimeters. Okay. So this is what we have to do now in the questions. So I'm just minimizing this for you to understand and then apply this. Okay, so remember the distance d was 75 centimeters, okay, in this. So delta t you have to find out, given that the distance d was 75 centimeters, such that your net amplitude comes out to be this 2.8 millimeters. This was the first part of the question. Okay, so you just work out how much delta t should be known from here. Now this should be fairly easy. So hope it is clear up to the equation of wave 1 and equation of wave 2. And why in the equation of wave 2 we are replacing kx with k of x minus d, because you know that source itself is at x equal to d. So you can see here that as far as the second wave is concerned, the source is at a point like this at x equal to d. And now we are looking at a general point like this at x equal to x. So this wave which is traveling from like this, it's traveling how much distance in this direction? It's traveling a distance of x minus d. So that is why this k term has come with x minus d. Whereas also the source started with a delay. It started at a time delta t. It didn't start at t equal to 0. So that is why this is coming. The source was started at t equal to delta t from the mean position. So the source is an oscillator from the mean position, but the time for that oscillator is not counted from t equal to 0. It is counted from delta t. Hence that equation. Right. So let's understand this further now. So we want that the net amplitude should be A1 plus A2. For this, the condition is that, remember, net amplitude is this now. It is root of A1 square plus A2 square plus 2A1 A2 cos delta phi. So for this here, the condition is that delta phi should be either 0 or 2 pi or like that. So here, if you now compare what is our delta phi, by comparison, you will see our delta phi is kd minus omega delta t. This is. We just go back one step here. Compare this equation. So in this equation, just compare this part to this part. You will understand. Right. So by this comparison, you can see that your phase difference delta phi is this. So once we have understood this is the case, so back here, we can see that it can become 0. In general, it is 2 and pi. But here the smallest value of delta t for which this will happen. So therefore, we are seeing that delta phi can become 0 for ED to become equal to omega delta, or delta T to become equal to D into E by omega. Okay. Or you can see that this is D into F lambda. Okay. So that distance was 75 centimeters, so 0.75 meters, multiplied by the frequency was 200 hertz, multiplied by the wavelength was 1 meter. So this should be pi. K is 2 pi by lambda and omega is 2 pi f. So it should be f lambda in the denominator. So 1 upon frequency. So 0.75 by 200 seconds. So we can also write that as 0.375 into 10 raised power minus 2 seconds, or 3.75 milliseconds. So if we give this much of a delay, we can have constructive interference. So this is the condition for this question. Right, so people hope this question is fully clear. So that is about interference of waves. Now, one more thing we'll look at before we come to standing waves is reflection of a pulse or a wave from a boundary. For example, if we have what is called a rigid boundary, like this. So this is a fixed or rigid boundary like this. Okay, then a traveling pulse of this type, after reflection from the boundary, it inverts and comes back. So the reflected pulse now has an inverted shape like this as it returns. So there is what we call phase inversion. When the boundary is rigid, whereas if we have what is called a soft boundary, like this kind of a situation here. This is like a smooth pole which is fixed, but the thread so this is something like a ring that can go up and down smoothly on this. So then this becomes what we call a flexible or soft boundary, because as you can see the surface of the pole is smooth, so it does not offer any resistance to the motion of the ring in the vertically up and down direction. So any transverse disturbance created from here, the motion of the ring up and down because of the transverse disturbance is not at all hindered by the boundary. So it becomes what we call a flexible boundary. So here, if we have an incident pulse like this, as you know, it returns in the same phase. In fact, here what happens is as it so as this pulse comes and hits against the boundary, first something like this will happen. Then something like this will happen. Then again it will come back to this position. Then again come back to this position, and so it goes and then returns back like this. And eventually, when it returns back, it's in the same phase. There is no phase inversion. So this is an important concept, and we'll see its application in certain types of questions also next term. So the two types of boundaries. Okay, so this will become very important for us in standing waves also, but before that, just on its own as a concept, okay, good. So let's look at a direct application question of this, then we'll come back to standing waves. That is next. So now we have a situation like this. So this is comparatively heavy gauge rope, and it has mu1 of, let us say, 9 gram per centimeters, and this is a comparatively light gauge string which has linear mass density of, let's say, 4 gram per centimeter, and this is the junction where they are knotted together, tied together. Now the combination is at a tension T equal to 1000 Newton. It will be a common tension as you can see. Now what is happening is from here, an incident wave y1 or yi of amplitude four millimeters and frequency 100 hertz is started from a large distance to the left of the junction of the two threads. So find the amplitudes frequencies and wavelengths of the transmitted and reflected waves. So I'll explain what this means. So what will happen is, okay, so what's happening here is this incident wave, as it is coming on this rope and hitting the junction point over here. So the junction point is going up and down as a result of it. So it acts like a source of its own. So that also creates a reflected wave here and a transmitted wave over here. So the disturbance that you are creating as a source somewhere over here, which is creating an incident wave like this, that is causing the junction point to go up and down, oscillate, and the oscillation of the junction point is creating reverse reflected waves in this medium and forward transmitted waves in this medium. So we have to calculate the total, we have to calculate the amplitudes, frequencies and wavelengths of the two types of waves that are created as a result of the oscillation of the junction, the reflected waves and the transmitted wave. So in solving this, I'll give you a hint. There are two concepts that we use. Okay, so the concepts that we'll use here is conservation of power. So the power of the incident wave should be equal to the sum of the power of the reflected wave and the transmitted wave. So that is one thing we'll use. And the other thing is we'll use the concept of reflection at a boundary. Okay, so for reflected waves, okay, in the heavier medium, the junction point acts like a flexible boundary for reflection of the incident wave. So any wave is a series of pulses. So what we had seen is at a flexible boundary, this is what happens, it comes back like this. So now a wave is a continuous series of pulses like this. One going like this, then one going back, then one like this, So they will all reflect back in phase over here without any phase inversion, because it is a reflect, the string on the other side is lighter compared to this one, so it is not going to offer any sort of it's not going to offer any resistance because its inertia is less than this. So this point can go freely up and down. It is not hindered too much by the lighter string on the other side. So it will act like a soft boundary or a flexible boundary. So using these two concepts, we will develop the equations required to find out the unknown quantities. So I'm minimizing this a little bit more so that you can see the whole question. So this is what we are going to work on next. Just try out this question. So this is probably the trickiest type of question for this chapter, waves on a string, and more exclusively a type of question which you can expect probably at JEE advanced level. Okay. So anyway, let's see how we'll resolve this question. So here, see, what we can do is we can take any type of notation we like. So what I will do is I will denote the junction as x equal to 0. I'll take my origin over here, the junction. And this is my positive x direction. This is having mu2, this is having mu1. So first of all, let me sort of write an equation for the incident wave. The incident wave's equation becomes some E sine omega t minus kx, where omega is 2 pi f and frequency was 100 hertz. K is 2 pi by lambda, where f lambda is equal to the speed of the wave in this medium, that is square root of t divided by mu1. So 100 hertz into lambda is equal to square root of 1000 divided by 0.9. So lambda is becoming 1/3 of a meter, or approximately. Okay, like this. I've taken the tension to be 1000 Newton, taken mu1 to be this much, so that is 0.9 kg per meter. This is 0.4 kg per meter. Okay, so from this we have K is 6 pi radians per meter for this equation. So these are my omega and k terms for the incident, and deliberately I'm just taking phase constant to be 0. So okay. Now what is happening is, let the reflected wave have amplitude equal to AR. Okay, so equation of the reflected wave will become y reflected is equal to that amplitude into the same omega, because it's ultimately caused by the oscillation of on the string because of the incident waves. So the incident phase frequency is going to be the same as the reflected and transmitted waves, but only direction of propagation has become opposite. Okay, and let's assume some kind of phase constant, which I will work out how much this is. Okay, so the plus sign here, this plus sign is coming because it's going in the negative x direction. The propagation of the wave is in the negative x direction. So that is one important thing. Now let us work out what is the value of the phase constant. Okay. So now we'll understand that the junction is acting like a soft boundary. At the point x equal to 0. So So what is happening here is at the point x equal to 0, imagine you have a pulse coming as a result of the incident wave. So it should come here. Okay, and then the reflected pulse should be in the same phase as the incoming one. Okay. So at the junction x equal to 0, the disturbance created by the incident wave is nothing but E incident sine omega t. Okay. I'm just substituting x equal to 0 in the incident waves equation. And the disturbance created by the reflected wave, so again in the reflected wave equation put x equal to 0, is some amplitude A reflected into sine omega t minus kx, so that kx term, sorry, plus kx, but that plus kx term becomes 0, plus phi. Now what should happen? This and this should be in phase. Okay. So y reflected at x equal to 0 should be in phase with respect to y incident at x equal to 0. Why this should happen that they are in phase? Because we are having a soft boundary for reflection. This term and this term should be in phase. So phi in general should be 2 and pi, or in this case let's just take it as 0. So therefore my reflected wave has the equation E reflected into sine omega t plus x. Okay, whereas the incident wave had the equation E incident into sine omega t minus x. Okay. So this we know now. Okay, and let the transmitted wave have the amplitude E transmitted. So its equation is some amplitude AT into sine same omega but different phase constant. So let's say k prime. Okay. So this will have same as incident wave, because the incident wave is acting like the source. Okay, but k prime equal to 2 pi by lambda prime, where that same frequency into lambda prime is some different speed, because it is square root of t by mu. This term. So the reflected wave has a same frequency but a different wavelength, okay, which is now given by this formula. So you can see that 100 hertz into lambda prime becomes square root of 1000 newtons divided by 0.4 that one was. So lambda prime here will become half a meter or 50 centimeters. So there is a slight difference, as you can see. Let's share this just a moment. I'll put the whiteboard back on this one. So there is a slight difference between the reflected wave and the incident wave, or the reflected wave and the transmitted wave in terms of wavelength. Okay, so your reflected wave is like this. It's having a different key. So the equation of the reflected wave was like this. Sorry, the transmitted wave was like this. So now through this we have written two separate equations now. The reflected wave and the transmitted wave. So I will just leave you with these equations for a moment to analyze this. So first understand it for the reflected wave. Okay, so in these two equations, your omega is 2 pi f is 200 pi radians per second, and your k is 2 pi by lambda, or it was 6 pi radians per meter. That was for the incident and the and the reflected wave, both. Both the waves which are coexisting on the heavier gauge string. The incident wave which was created by some source and the reflected wave that is coming back. So those two will actually superimpose on the heavy string. Whereas on the lighter string, you will have only one wave which is going, which is the transmitted wave. Alright, so as you can see, we've got the equations of the waves. Now we have to, the two unknown quantities for us are this thing, the reflected waves amplitude and the incident waves amplitude. To find frequencies and wavelengths, we've already found out now. We still have to find the amplitudes. Incident waves amplitude is known, 4 millimeters. So for that, we'll use the two concepts that we are discussing: the power conservation and the continuity sort of equation. So conservation of power. The incident waves power should be equal to the sum of the transmitted waves power plus the reflected waves power. Now remember, power of a wave was given by this formula we discussed last time: half mu v omega square a square, or you can also write this as half square root of p mu into omega square, because of course v in this equation is square root p mu. So from that, let's use this second equation, it will be easier. So half square root of, now the incident wave is existing in the string of this thing, string 1, omega square into a incident square. Transmitted wave is existing in the second string. All of them are having the same omega, and the tension is also common in both the threads, that you can understand from the free body diagram of the junction. Now the reflected wave is coming back in string 1. So this is mu1. This is mu2. So the incident wave and the reflected wave, they are existing in this, whereas the transmitted wave is existing in this one. So this becomes a power transfer. Okay, so square root mu1 into incident square is equal to square root mu2 into transmitted square plus square root mu1 into reflected square. This becomes like my first equation, which is coming from power conservation. So here you substitute mu1 as 9 gram per centimeter and mu2 as 4 gram per centimeter. So this becomes this equation. Now with A reflected and A transmitted. So we need one more equation. So where is that equation going to come? So that equation is going to come from a sort of equation of continuity. Okay, so yeah. Secondly, we have a sort of continuity equation. At the junction, that's x equal to 0. So what I mean by the continuity equation is that the junction does not snap, it remains intact. Okay. That means at any point of time, or the junction, since it should not break. So the left and the right hand side limits. So sort of limit that we are applying, the delta x tending to 0. That is, the junction should remain intact. So it should not become like this, that the left hand side of the junction is like this and the right hand side is like this. They should at the left hand at the left limit placement at the right hand. That's it. Now you can see that on the left hand side, the net displacement plus right hand side y incident at x equal to minus y equal delta x tending to 0 at x equal to plus delta. It's a little bit tricky. My junction point is x equal to 0. So उसके left hand side पे क्या हो रहा है? The net displacement is occurring is the sum of incident and reflected, because those two kind of waves are superimposing, whereas the wave is propagating. So the right hand limit is nothing but the value of the transmitted wave at delta x tending to 0, whereas this is the value minus delta x, limit delta x tending to 0. So now we need to solve this limit. Okay, so we need to solve. Incident was E incident sine omega t minus kx. Okay, so delta x tending to 0 it will be this. Plus reflected was E reflected sine omega t plus kx. But my delta x is tending to 0, so it's this. Okay. This should be equal to, on this side it was the transmitted wave, so it was E transmitted sine omega t minus k prime delta x, but again delta x is tending to 0. So this becomes my second equation. Okay, this is coming from the fact that there is continuity at x equal to 0, because the junction does not snap. That property. So I'll just minimize this because there's a tricky concept here. Just make sure you go through this. Okay, so let's understand what we got from these equations now. So this sine omega t is just common everywhere. So this actually gives us that E incident plus E reflected is equal to A transmitted. So this is our second equation. Okay. Right. So we'll just check that, Maniska. Now, so let's just check on the equations that we have. This one we have that 3E incident square is equal to. So we also have so we'll substitute this in over here. And of course, E incident was 4 millimeters. So we have 3 into 4 square is equal to 2 into E transmitted, which we can write as 4 plus square, okay, plus 3 E reflectors. So substituting this. So now it's a matter of just solving this out. So we got so we've got 3 plus 5 ER square plus 16 A reflected minus 48 plus 32. So 16. Alright, so from this we can just work it out further. So we will not be taking the negative root because amplitude is a mod quantity. So we will avoid the negative root altogether. And then going back there, the transmission amplitude becomes the sum of this and this. So becomes count these, and the wavelength for the reflected was 1/3 of a meter. wavelength for the transmitted was half a meter. Frequency of that was common for both. 100 hertz. So these become the solutions. Right. So that is this particularly tricky type of question, which is to do with reflection and transmission. Other than that, what is another application of reflection at a boundary, but continuous reflection at a boundary is the case of standing waves. Just hang on a second. I'll refresh the whiteboard. Oh. So the general concept of standing waves. So these are resonant modes. This is something very standard. I'm sure all of you are aware of this. So if we have a string which is between two rigid boundaries, like this here and this here, they are fixed ends. And the string has a length L, tension T, linear mass density mu. So you can see that the different modes of vibration possible here for the string become like this. So the fundamental mode looks something like this, where you have two nodes like this. So for fundamental mode, the length of the string L becomes the distance between two consecutive nodes. Okay, so the frequency becomes 1 by 2L square root T by. Then, for example, for the first overtone, string vibrates like this. As the midpoint of the string also acts like a node now. So the first overtone mode, the length actually becomes twice of lambda by 2, or lambda becomes equal to L. So the frequency of the first overtone becomes 1 by L square root T by V. So you can see that the first overtone is equal to 2 times the fundamental. So we say it is the second harmonic. So here in this language, we say that the first overtone has a frequency that is equal to second harmonic, or second multiple. Harmonic is basically the multiple of the fundamental frequency. So like that, for example, the third overtone mode, that will look something like this. The boundary points become third consecutive nodes. So in the second overtone mode, this length is becoming 3 times lambda by 2. So the frequency, the second overtone becomes 3 by 2L, because lambda is 2L by 3, square root of T by. Or the second overtone becomes the third harmonic. And like that, we have a general case that in the what we call the nth overtone mode, we have n plus 2 nodes, or n plus 1 antinodes. Or in all, we have n plus 1 loops, you can say. The string looks like n plus 1 loops. So this L becomes n plus 1 lambda by 2. So the frequency of the nth overtone becomes n plus 1 by 2L square root of T by, or n plus 1th harmonic of the fundamental. So this is the general formula. First overtone is second harmonic, second overtone is third harmonic, like that we see. So the nth overtone mode has a frequency equal to the n plus 1th multiple of the fundamental, or what we call the n plus 1th harmonic. So this is the general description of this. Okay, so this is this type of standing wave. So let's look at a quick question based on this. So now we have something like this. Let's say. So we have a kind of heavy rod which is suspended by two lighter ropes, threads. This. So these are threads of identical length and mass, but the mass is negligible. Compared to the rod. Okay, so this is a heavy rod, uniform heavy rod, which has mass, let us say 50 kilograms, and length of 100 centimeters. Okay, now what we are also doing is to that we are attaching somewhere over here a block kind of thing. Of some mass m prime, but at a distance d from this end. Of 40 centimeters. Okay. Now what we want is that when we bring in a tuning fork of a certain frequency f, it resonates with both the strings. The same tuning fork of frequency f resonates with both the strings. Okay, so let's say this is thread E and this is thread B. So now a certain tuning fork resonates with both strings E and B such that its frequency f matches the sixth and fourth harmonics of the fundamental for E and B, the strings or the threads E and B. Sixth harmonic is the same thing as fifth overtone. This is the same thing as third overtone. So another way of saying the question would be that it matches or it resonates with the fifth overtone and the third overtone of the strings A and B respectively. Okay. So we have to find the mass m prime that we've added here. So this is the typical type of question related with standing waves, but with a bit of mechanics added in. Just try this out. So you realize because the mass m prime is closer to the side B compared to the side A, so it will create more tension in the string B compared to the tension in the string A. So more tension in B means that the fundamental frequency of B is more than the fundamental frequency of E. So that is why the same tuning fork F is matching only the third overtone of B, whereas it's matching the fifth overtone of E. From that we have to understand how much mass m prime is the blocks. Okay, so you can just do like this, take the tensions TA and TB or T1 and T2, and from that write the formula of the fundamental frequency of A and the fundamental frequency of B. Now whatever A is fundamental frequency, the fifth overtone or 6 times F0 of E should be equal to the frequency of the tuning fork. And again, whatever the fundamental frequency of B, let's say F0 prime, 4 times of that or the third overtone of that should be equal to the same frequency of the tuning fork. So from that you will get some relationship between the tensions, and from that relationship between the tensions you will get the idea about where this is attached. I mean how much mass is attached. You will get another relationship for the tensions by doing torque balancing.
Dreaming about being big time. Just a young gun with a quick fuse.
Yeah, so from that you should, Manishka, you should now be able to get the relationship. Okay, so what is happening here is you can see that for string A, the fifth overtone for E should be equal to the third overtone for B should be equal to the frequency of the tuning form. Okay. So from this relationship, 6 times 1 by 2L square root of TA by mu should be equal to 4 times 1 by 2L, because they are having everything else identical. Length is same. Only the tension is varying because the mass is not symmetrically distributed. Otherwise, they are identical states. So this is telling me that square root of PA by TB is 2 by 3. Or TA is to TB is 4 is to 9. This is my equation 1. This is the waves part. Now the rest is mechanics. Now the rest is mechanics. You just make the free body diagram of the rod and you will understand. Now for the rod, you can see that two tensions acting here, its own weight acting through the midpoint, and the weight of the other thing acting like this. That's it. Now you can take TA, suppose as 4x. So TB is 9x. So TA plus TB is M plus M prime G. So 13x is equal to, mass of the rod was I think 50 kilograms. Okay. And you can do now torque balancing. This is, the rod's length was 100 centimeters. So this is 50 centimeters. This is the midpoint of the rod. And this is 10 centimeters. This is 40 centimeters. So for example, let me do torque balancing about this point. It will be very easy. So net torque about E is equal. Suppose I do that. Okay, so you can see that mg into 50 clockwise plus m prime g into 60 centimeters. We don't have to convert to SI unit as long as we are consistent on both sides, is equal to tension TB into 100 centimeters, which is the anti-clockwise torque. You can talk about C also, it doesn't matter, or about this point also, but I'm just writing in a very convenient way here. So 5 mg plus 6 m prime g is equal to 10 times TB, which is 9x. This becomes your second input. This. So currently we are getting x as a negative quantity. Currently we get x as a negative quantity, 50g is equal to minus of 12x. Okay. So that means this is not possible. Okay, so let us change something in the question so that this becomes possible. So if we change the value of d now, okay, so I'm changing d. So basically the negative x is showing, you see, if x is negative, it is not possible. So that means it's not possible to have this equation for the given distance d, no matter how much mass m prime we attach. Okay. So let's change the value of d. So if d is now changed to, let us say, 10 centimeters. Instead of this. Yeah. Okay. So suppose we change d to 10 centimeters. So then this goes here actually. Okay. So this becomes 10 and this becomes 40. So from here the moment arm becomes 90 instead of 60. So let's see how that changes our equation. Okay. So this becomes 9. Whereas that equation remains the same. So we will have to multiply this equation with 9 now. So when we multiply this equation with 9 instead, now we'll see that we'll get 450 minus 250, so that's 200g. is 9 into 13 minus 90. So that will become 27x. So this will give us the correct value. So x is equal to 200g by 27. So going back to this, now m prime will come in terms of this. So from this now, we have this relation. So we have m prime as what? We get this one. So it just means that it was just not feasible. If we keep that mass m prime attached at that kind of distance, okay, it is just not feasible for the ratio of the tensions to be 4:9, which we are getting. Okay. Whereas if we shifted to 10 centimeters from that end instead of 40 centimeters from that end, it is feasible, and for that the mass value has to be this much. So this type of question related to this. Okay. So I'll just take you through all the steps from the beginning once. So this was the question in the first place. Only this D now I changed this. Okay, so from 40 centimeters I flipped it, made it 10 centimeters. Okay. Yeah, so changed it to that. Okay. Right. So now the same tuning fork, as you can see, is giving different harmonics with respect to A and B. It's resonating with the sixth harmonic or fifth overtone in A and the fourth harmonic or third overtone in B. So you have to find the condition on the mass M prime. So first you start with this concept over here, that the same tuning fork's frequency F is resonating with the fifth overtone here or the third overtone here. So fifth overtone is sixth harmonic of fundamental. So we are using this formula that nth overtone of the fundamental is n plus 1 times the fundamental, or n plus 1th harmonic, or n plus 1 by 2l square root of t by nu. This formula we are applying. So we are applying it to both of these simultaneously. Okay. So from this, since the strings are identical, so they are having same length and same linear mass density, only the tension is different. So the ratio of tensions is coming. And once you got the ratio of tensions, the rest is a mechanics problem. That how would you place some unknown mass m prime such that, yes, these are right? So this is the completion of this. Okay, now another type of situation of standing waves of a string would be something like this, that one boundary is a rigid boundary, whereas the other boundary is a soft boundary. That could also happen, though it is a little bit more unusual in the case of strings. We will just take a 1 minute break. Yeah, people, I think my system has got hanged a little bit. That's why in between audio is also not. So just take a 1 minute break. I will have to reboot my modem. Okay, just. Okay, people, back online with the whiteboard in just a moment. Yeah, so I was telling you there's one more kind of situation which we can see in strings case. So this is a fixed boundary. Okay. But here on the other side, we have let us say that flexible kind of boundary. We have a smooth fixed pole. We have a ring kind of thing over here. And this thread is of length L, tension T, and linear mass density. So what happens here is this acts like a antinode, because it's a flexible boundary, so it can move freely. So there'll be maximum displacement at that point, whereas this acts like a node. So here the fundamental mode looks like this. Okay. So node antinode. So the fundamental mode lambda by 4. Okay. So the fundamental frequency has a formula 1 by 4L square root T by mu. Okay. Now similarly, the first overtone here, now this will look like this. So antinode, node, antinode. So it is lambda plus lambda by 2, or the length becomes 3 lambda 1 by 4. Lambda 1 by 2 plus lambda 1 by 4, like that. Okay. So the frequency of the first overtone becomes 3 by 4L square root T by mu. So here you can see the formula is different. The first overtone is the third harmonic of the fundamental. Second harmonic does not exist. So in general, the even harmonics don't exist over here. The second overtone, for example, will look like this now. So it is lambda by 2 plus lambda by 2 plus lambda by 4. Okay, so one by 2 plus 1 by 2 plus 1 by 4, or as you can see, 5 lambda by 4 becomes the length of this. So the frequency becomes 5 by 4L square root T by mu, or the frequency becomes fifth harmonic of fundamental. Okay, so like that, in the nth overtone mode, this length becomes half plus, like this. So this is n terms. So L becomes 2n plus 1 lambda by 4. So the frequency becomes the 2n plus 1th harmonic of the fundamental. So this is the general formula. So the frequency, the modal series is like this, all the way to. So in this kind of situation, we say that only odd harmonics exist. The even harmonics do not exist. So this becomes the general series and the general formula. Okay, so people, with this you should be able to complete everything to do with the first chapter of waves, the first part of waves, which is transverse waves on a stretched string. Now we'll take a few more minutes today and we'll look at the beginning part of sound, so that you can get started on sound also. Whereas the part of sound which is going to be very different, which is Doppler's effect and beats, that we'll finish up in the next session. So sound, or what we call longitudinal waves. Or later we'll see, we also call these as pressure waves. Okay. So one dimensional longitudinal waves, the physical model would be that you have an air pipe, or what is more traditionally called an organ pipe, coming from the church organ instrument, which had air pipes to propagate sound. Okay. But only this is going to infinity, so there's no question of reflection coming back. So here, so if you have a wind pipe or an air pipe, narrow one, okay, and we have some kind of a source which is creating vibration like this, okay. So you could even think of the source like a diaphragm going back and forth, but here I will take the source like a tuning fork, whose prongs are vibrating back and forth like this at a fixed frequency and amplitude. So what they create is disturbance like this. So that disturbance is carried along the string. Okay. So if we take this as our x-axis, okay, so we can see if this is x equal to 0 and this is some general point x equal to x. So at x equal to 0, okay, the tuning fork, which is acting like the source, it's creating an oscillation okay, along x-axis only. So hence the term longitudinal. The particles are actually vibrating with displacement from the mean position along the same axis as the propagation of the wave. So the wave is propagating in this direction with speed v. This is also, so it is along x-axis, or what we call longitudinal, given by s at x equal to 0 is some amplitude s naught. Now we can write that as a also, it doesn't matter. Omega t plus, let's say, some phase constant, fine, where omega is again 2 pi f. F is the frequency of the source. Okay. So again, like transverse waves, we'll see frequency is a property that belongs to the source, whereas wavelength, we'll see later, is affected by both the source and the medium. Okay, so this is the disturbance that is being created at x equal to 0. So at any general point, P, let's say, where x is equal to x, okay, the disturbance reaches after a delay. So because what is happening from x equal to 0 to x equal to x, the disturbance is starting here at t equal to 0. It has to travel through a distance x with a speed v. So it reaches here at some time delta t, which is equal to x by v. So this particle or this set of particles also start vibrating with the same properties as this, but this started at t equal to 0. This started after a delay of delta t. So s at x as a function of time becoming s naught sine of omega t minus delta t plus phi naught, where that delta t is nothing but x by v. And how I know v is constant? Because the medium is having uniform properties. And whatever the air or gases or whatever fluid medium is filled over there, it is having uniform properties or isotropic properties. So we'll assume that the wave propagates at a uniform speed. So as you can see here, s becomes some amplitude into sine of omega t minus omega by v into x plus phi naught. So this omega by v into x, this term is what we call k, okay, or we have the wave speed equal to omega by k, okay, which is f lambda. So again we have this time the wave propagation speed depends on the Bulk's modulus of elasticity and the volume density. So for sound in ideal gas medium, okay, taking the propagation of sound, as you know, as the process of propagation of sound is treated as adiabatic compressions and rarefactions. So adiabatic Bulk's modulus, you know, is gamma p, because you have pv to the power gamma is constant. So gamma pv to the power gamma minus 1 dv plus v to the power gamma dp is 0. So from that, Bulk's modulus, which is minus dp divided by dv by v, becomes gamma p. Okay. So therefore, square root of Bulk's modulus upon density becomes square root of gamma P by rho, and further you use the relation that ideal gas in modified form. So you substitute that. So the speed of sound in an ideal gas medium becomes root of gamma RT by M. This is in gaseous medium. Whereas we should also understand that speed of sound in liquid medium is just given by this, or what we can say ideal fluid kind of medium, like water, etc. Whereas also speed of sound in solid mediums is square root of Young's modulus by density. So these are the three separate formula for speed of sound. Okay. So this is about speed of sound. But anyway, now coming back over there, whatever the speed of sound, that is equal to F lambda or omega by K. Okay. And the equation, the displacement, okay, wave equation becomes S at x at time t becomes some amplitude into sine omega t minus kx plus some phase constant. And in fact, if it is traveling in the opposite direction, it will just become omega t plus kx. And similarly, you can replace it as kx minus omega t plus phi naught plus pi, or you can even replace it in terms of cos. So all that is same. So this is the first part, how we represent sound as a traveling longitudinal displacement, okay, which has a certain longitudinal displacement amplitude S naught, a certain frequency F, which is the frequency of the source which is creating it, but which has a wavelength lambda, and that wavelength depends on the properties of the medium also, because we have that lambda is equal to V by F, and V is the property of the medium. So it is square root gamma RT by M for gas, the square root of Bulk's modulus by density for fluid, and it is square root of Young's modulus by density for solids. So V is a property of the medium, F is the property of the source, and lambda depends on both source and medium. So that common strain of logic remains over here. That was that. Okay. Now, through a somewhat more lengthy derivation, you can also show the pressure variation that happens at any point as a result of that. So the displacement wave also creates a pressure variation, or you can say volume stress. So what is happening is, within your longitudinal medium like this, if you consider a section of air like this, because of the vibrations back and forth, this is alternately expanding and then compressing, and again expanding, then again compressing. So it undergoes alternate compressions and rarefactions. So we just apply the concept that consider this section which has a natural thickness of delta x. So the natural volume V, you can say, is this area is E times delta x. Okay. So at any instant, it has a strained volume. It's undergoing volume strain V plus dV, which you can say becomes E into delta x plus dx, because the length alternately expands, contracts because of the compression and rarefaction which is happening over here. So the volume strain is dV by V. So that is just becoming E times dx divided by E times delta x. We just compare this equation with the equation we have written above. This one and this equation to understand how this happens. Okay. So that is dx upon delta x. Now, why is this dx occurring? Because there is displacement. So we can see that this dx is due to longitudinal oscillation given by this displacement formula. This kind of formula. So ds or dx is nothing but basically a small displacement along the x-axis, which we can write as del s by del x times dx. So just applying the partial derivative here becomes minus s naught k cos omega t minus kx. That's fine. So this is my ds. So therefore, in fact, we should think of this like this last term here. You should think of it like a delta x. Okay. So ds is rate of change into delta x. Like that. So coming back to our volume strain, which was dx by delta x. You can see you substitute that in over here. It becomes minus s naught cos or s naught k cos omega t minus kx. That's fine. Therefore, volume stress which you can write as delta P, which is minus of bulk's modulus into volume strain. So here we write the volume stress on the SP, but you should understand that it's actually a pressure variation. We write it as XT. Okay. So that quantity is minus of beta into volume strain. And we just saw the volume strain above. So the pressure variation or the excess pressure at x as a function of time becomes beta k into s naught into cosine of omega t minus kx plus phi. So this quantity is what we call the pressure amplitude. So that's bulk's modulus into k into s naught. So the pressure variation at x as a function of t becomes some amplitude into, we can write this now as sine omega t minus kx plus, let's say, phi naught plus pi by 2 compared to the displacement, which does not have that pi by 2. Because displacement was sine, here this was cos. So to convert sine to cos, this is the relationship between the displacement equation and the pressure equation. So generally we choose to understand sound as a pressure variation. So actually both the things are happening. There is longitudinal displacement occurring, which is causing pressure variation. So this is sound as a pressure wave. Okay, and this is sound as a displacement wave. So you can see that they have pi/2 phase difference and amplitudes which are given by proportionate amplitudes. P0 is proportional to S0. So this is the fundamental part to understand about how to describe sound in terms of equations, sinusoidal equations. So all this is of course should be there in your theory notes, or you can refer to HCB or whatever. Given it in quite a lot of detail over here. But for you, this result is the more important thing. Okay? And along with this result, now already we've discussed about speed of sound, but also the important thing is the this thing, intensity. So here instead of power, we describe intensity of sound, which is basically power per unit cross-sectional area, or it is energy transmitted per unit time, per unit area. So that intensity comes out to be a very similar formula as the power in the case of the strings. But here it comes out to be half. There it was mu v, here it is rho v. So linear mass density is replaced with volume density into v into omega square into displacement amplitude square. Or you can see, you can also write the intensity as half square root of Bulk's modulus into density into omega square into S. And in case it is sound propagating through a gaseous medium, it always replace Bulk's modulus in terms of gamma p. So that's fine. So this becomes the formula. But more importantly, you can see that intensity is proportional to displacement amplitude square, all other things being constant. So intensity, that means, is also proportional to pressure amplitude square, because displacement amplitude and pressure amplitude are proportional. So this becomes important. Okay. And from this point, you have the two common things of sound with respect to transverse phase, which we had seen till now, which is interference and standing waves. Okay. So you can go ahead and complete your revision problems, whether you're doing from HC Verma in sound. HC Verma is excellent. In transverse waves, it is a little bit short of questions, so you should definitely supplement HC Verma with something like your booklet will do, or DC Pandey or something like that. Even in sound, you can supplement with DC Pandey, is fine. But HC Verma is sufficient actually for the sound chapter. Okay. So you can complete problems up to interference and standing waves in sound, because it's the same concept again of path difference and phase difference. And in case of standing waves, there are two types of situations. One where both the boundaries are identical, so you have both the boundaries are identical, so you have both even and odd harmonics, that formula, like we saw the first case today, with both the boundaries being fixed. Whereas you also have what we call open organ pipe, where one end is open and one end is closed. So that acts like the situation where one is a flexible boundary and when one is a rigid boundary. So node and antinode. So there only the odd harmonics exist. So that is the same type of formula as we saw for the second case of standing waves on a string. Alright, people. So with this, we are completing today's lecture. Just a second. Right. So with this, we are completing today's session. And next time, as I told you, we'll concentrate more on beats and Doppler's effect, which is the variation part of sound, and we'll complete that with it. Okay. So hope you people have understood this. I will send you the recording of this so that you can refer to it for notes and all that. Okay. And that's it from my end today. Bye and wish you all the best.